Hello, welcome to the next video in the series of Physics at Home. So much for Physics at Home. This video actually incorporates some items which are not usually found at home. So this one is more as a demonstration of what you would see in some kind of a face-to-face lab at a university or a college. Okay. So what we have here today is here is a force table. And today what we're going to learn is essentially Newton's first law of motion. Now everybody probably have heard about this statement that object at rest stays at rest, object in motion stays in motion until acted upon by a force. So this statement, it's pretty easy to understand, but actually Newton's first law sometimes could be a little bit tricky to have an intuition about. Okay, so what we are gonna see is what is at the heart of the Newton's first law, and that is if there is an object and then if there are multiple forces acting on it, if they all add up to 0, then the object is gonna have 0 change in velocity. Okay, so if the velocity is 0, it will stay at 0. If the velocity is, let's say, 5 meters per second along positive x-axis, then it will stay 5 meters per second along positive x-axis. Okay, so the object in interest is this ring. Okay, so this ring here has 4 strings attached to it, and what we're gonna do is on these strings we're gonna attach some masses using a hanger. So as you can see, this hanger here is about 50 grams, and I could attach this hanger here on this string, and then when I let go, okay, so if I let go here, then it is going to pull the string in that direction, correct? So I want to make sure that this is being pulled at a certain direction. To specify which direction it is going to be pulled, I'm going to use a pulley. So this pulley here, this line, is going to help us decide, or specify which direction the force is going to be pulled. So this line here, if you align it with the numbers along this protractor, then, let's say for example, right here, now we fix it, this pulley, then this is at 90 degrees. So if I place the ring here and now put the hanger going over on that side, now you can see it is suspended and it is pulling the ring in that direction. Okay. Now remember, we want all of the forces acting on this ring to be 0. So if I want to balance this 50 grams that's been pulling in this side, then I would be adding 50 grams in the opposite direction, correct? So if I add 50 grams at 270, right? So then that will balance this out. Okay. What we're gonna do is we're gonna add some mass at 0 degree and some mass at 90 degree. Okay. So there is some pull along this direction and then some pull along that direction. And then what we're gonna do is figure out if we had to balance these two using just one, somewhere in this direction. Okay, so let's see the setup, how this is gonna look like. Okay, so now you can see a setup here where I have one pulley at 0 degrees and another pulley at 90 degrees. Right now there are no masses attached. Okay, what I'm gonna do is I'm gonna add 50 grams at 0 degree position. Alright, so 50 gram is here, and then I'm gonna add 120 grams. Okay, so 50 plus 50, so makes it 100, and this right here is a 20 gram. I don't know if you can see this, but yeah, 20 gram. Okay, so 20 grams. So 120 is going over here. So as you can see now, the ring is being pulled somewhere in this direction, right? Because there's a little bit of pull, bit of a pull on 50, in this direction, and then there is a little bit of pull, in that direction. So we know that if we have to balance, right now there is a little pin here, this pin here, which I am putting in so that again, I don't have to keep holding the ring at the center. So the 50 gram here we could balance by adding 50 gram at 180 degrees, and then the 120 here I could put 120 and then balance it out, right, in that direction. But let's say I want to balance the 50 and 120 using only one mass. Okay. Then where should I put it? And sometimes, we think that, oh, probably it's 50 plus 120, so 170 gram, and right in the middle, right? Well, let's see, if I could get intuitively it's possible, right? So essentially the 270 and 180 is right here, so somewhere in between, right? If I try to pull, so you can see, in that direction it's not really working. I want to pull it more along this direction. Yeah, so somewhere over here I need to place a certain amount of mass so that now the ring will be balanced, right? So I could remove this and it will stay at that spot. So in the next section we'll see how much and where should we have that balancing mass. Here we see a schematic representation of the force table. Currently there is a 50 grams hanging by 0 degree position, and 120 grams is hanging at the 90 degree position. Now we keep mentioning that we are interested in the forces, and the force that we're talking about here is weight. Weight is mass times gravity. So mass in kilograms, and then gravity, which is 9.8 meters per second square. Now for all of these masses we will be converting kilogram and then multiplying by 9.8. So instead of that we can just concentrate on looking at how much is the actual mass, because the conversion to the weight as newtons by using this formula is the same. So let's just concentrate on masses. Alright, so mass A is 50 at 0 and then 120 at 90 degrees. What we want to figure out is these two masses together, what do they comprise to? So we are interested in this green arrow. This green arrow is the sum of the force due to mass A and mass B. So we are interested in the length of that arrow, also the direction of this arrow. And the way we can work this out is by considering this here a right angle triangle, for which the green arrow is the hypotenuse. And then if you're thinking about this angle right here, theta, then MA is the adjacent side and MB is the opposite side. Okay, but we already know the adjacent and opposite, so all we need to figure out is how much is the hypotenuse. And hypotenuse is going to be using the Pythagoras theorem, which gives us as the square root of the sum of the squares of A and B. Which, if we plug in our calculator, it tells us that this is 130 grams. Okay. So A and B together are as good as 130 grams, pointing in that direction theta. All right. So for this angle theta here, we can figure it out using any one of the sine, cosine, or tan. Okay. What I'm going to use is a tan function, and tan we know is opposite over adjacent, and the angle theta here, A becomes the adjacent side, and the blue here becomes the opposite side, which is nothing but B. So theta now is tan inverse of opposite, which is 120 over 50, the adjacent. And theta turns out to be 67.4 degrees. Alright, so this right here is pointing at 67.4 degrees. So these A and B together is 130, pointing at 67.4. So what we want is something pointing in the opposite direction with the same mass. Right there. And that right there is our balancing mass. Since this here is pointing at 67.4, if you add additional 180 degrees, then this balancing mass is supposed to be at 247.4 degrees. So let's see if indeed, if our calculation is correct, then we can balance the A and B using the mass C. Okay, so as we saw, what we need is a balancing mass of 130 grams. So 50 plus 50 makes it 100 plus 20. So that makes it 120 plus 10 grams. Okay. So 10 grams. And that 10 in 130 grams supposed to be at 247. So as you can see, the scale here is 0 and then 90 and then 180. So we gotta look at the outer scale. So the 240 is right here, and we cross 245, 246, 247. As you can see, I mounted a pulley here. Okay. And I'm gonna now mount this 130 grams in that direction. There we go. I can now take the pin out. And you can see now the ring is balanced. There's nothing here, it's just an additional ring. So right now on this ring, there are 3 forces, and they all add up to 0. So if the ring is at rest, it will stay at rest. Okay. If it is in motion, stay in motion, but we cannot demonstrate that part. But I believe we get the idea that all of the forces on this ring add up to 0. And that is the Newton's first law. So what this one is doing is balancing both of these out. Or in other words, this one pole in this direction is been balanced by 50 and 120. Yeah. So what happens? Okay. What happens now if I add 100 grams on this one? So instead of 130 pulling in this direction, now I have 230. So as you can see now, there is more pull than what these two can balance out. So now we want to reverse the problem. That if there is pull in this direction, how much should be this mass and how much should be this mass? Okay, so let's see in the next section of the video if we are able to calculate it. Okay, so now we are interested in increasing the mass C to go from currently, which is 130 grams. We want to increase it to 230 grams. Correct? So in other words, it looks like this. So the 130 grams is no longer there. Okay, now it becomes 230 grams. But as we can now realize, looking at this picture, that now the red line here, okay, this red line is not the same length as our mass A, correct? So mass A now has to increase by a certain amount. And in the same way, the blue arrow, which is pointing here, is not the same length as this blue arrow. So what we want to do at this point of time is figure out actually how much are these quantities or these arrows right here. So how much is this one and how much is this one? Okay, so as we remember, this here is theta 67.4 degrees. So is the same theta right here. So these are opposite angles. And now we can look at a right triangle right here. And the hypotenuse is the 230 grams. Then the horizontal side becomes the adjacent, and blue becomes the opposite side in that right triangle. So all we gotta do now is use our trig functions. Okay, so sine theta is opposite over hypotenuse. Okay, so we know angle theta and we know hypotenuse, so let's calculate the opposite side. So I'm going to do a cross multiplication here. So hypotenuse times sine theta equals to opposite side, and hypotenuse is 230, sine 67.4, that is equals to 212.3 grams. That is the opposite side. Okay. Similarly, cosine theta is adjacent over hypotenuse. So hypotenuse times cosine theta makes it adjacent side. And then 230 times cosine 67.4 turns out to be 88.4 grams. That is the adjacent side. So now these two here are our new masses A and B. Okay, so initially this is 50, but now it is increased to 88.4, right? So that means we have to add to our current setup 38.4 grams, and then for this is supposed to be added to A, and then for B we have to add, so earlier it was 120, but now it's 212, so about 92 grams, right? So 212 minus 120 makes it 92 grams. So that we now end up with this scenario, where now the mass B is 212 and mass A is 88.4, and these A and B, they are balancing the mass C. So as we saw that at 0 degrees, we should have around 88 or 89 grams. Okay, so we already have 50 hanging from the previous part of the experiment. So need to add, so that is 20 plus 5, 25, 27, sorry, 25, 30, 35, 37, and 39. Okay, so it's more than 88, so I'm gonna make it 89. I don't have half a gram, so this goes here. So 50 plus 39 makes it 89. And then on 90-degree position, we already have 120. So 140, 160, 180, 200, 205, 10, and 212. Okay, so let me add those. All right, so there we go. And remove the pin, and the ring again stays at rest. Okay, so this here now we can see the vector nature of the forces, that we cannot just simply add 1 and 2 and make it and get this one. What we need is the vector mathematics behind it. Okay, the vector nature, so the force which is just the magnitude and direction. Okay, now we're going to take this, and here's the question as we take this further. What happens if I bring this 230 grams and bring it to 270-degree position? Now the ring is being pulled, right? So right now these three, they're not balancing each other out. Now what we're gonna need is a fourth mass, and it should be somewhere here, right? So how much would that be? It's for you to find out. I hope you like this video. Next week we will meet to discuss the second law of motion, and to do so we'll be using what is called as Atwood's machine.